Electrical capacitance defined as a ratio of an isolated conductor might surprise you a bit. This is the definition. This is the electrical capacitance of an isolated conductor, and but it is a ratio. Capacitor would normally associate with limit. When asked what is the capacity of a vessel, you'd be talking of the maximum amount of liquid it can hold. So this ratio is a bit of a surprise. The closest you know is thermal capacity, which is also the amount of heat required per Kelvin raise of an object, of a conductor. So this kind of analogous. It's a ratio, not a limit. Well, let's elaborate that a bit later, but for the time being, let's calculate the capacitance of, say, a spherical conductor. Mind you, we're talking of isolated conductors. If there are any other charged bodies, they're very far away, so far away that we can consider that this particular conductor we are interested in is isolated. So, you assume a charge on the conductor, and in case of spherical conductor, you know the formula for the potential of the conductor. So you have this charge Q on the spherical conductor, and its potential V would be Q by 4 pi epsilon 0 r, where r is the radius of this conductor. Now the ratio C Q by V, you can see from here, comes to 4 pi epsilon 0 r. As simple as that. Now 4 pi epsilon 0 is a very small value, 1 by 9 into 10 power 9 units. So even for a fairly large conductor, this would be a very low value. Let's calculate the capacitance of the biggest conductor we can imagine, we know about. Well, the radius, the Earth. We know the radius of the Earth, 6,400 kilometers. So the capacitance would be 1 by 9 into 10 power 9 into 6,400 kilometers, right? So that will be another 3 zeros. So we are in meters here. This is 10 power 5, so 64 by 9. So this is 10 power 4, right? 10 power 5, so this is into 10 power minus 4. This is to about, say, approximately, this is a nice sign, you can round off things. We are really not very serious about the exact value, so we are trying to just get a feel of capacitance. 64 by 9, that would be, well, about 7, so let's say this is 7, make it 10 power minus 6, so this comes to 700 microfarads. Farad is unit, so coulomb by volt would be farad. So capacitance of a huge conductor like Earth is coming out to 700 microfarad. Now, that might surprise you a bit, because anything else with a big object you expect should have a big value. So you expect that any conductor should have a very, very small value for capacitance. But let me show you something. This one, it's not a conductor, it's a combination of conductors. It's called a capacitor, and it has a capacitance of 2.5 microfarads. Now, for Earth it is 700 microfarads, and you expect larger the size, greater the capacitance, because if the conductor is bigger, charge has more place to spread, potential would be smaller, and so capacitance will be greater. So this small object, this capacitor used in a fan, has a capacitance of 2.5 microfarads. That must be a bit of a surprise. It's almost like I show an object like this and say it is 1,000 kilograms. You would think I'm crazy, or you would think I don't know units. Now look, you know about volumes, densities, and for the size of this for for an object of this volume, it could be 5,000 kilograms or whatever I said earlier. Now, even if it were really 5,000 kilograms, I couldn't be holding it. If I were capable of holding a 5,000 kilograms of an object like this, then I would be in the Olympics. I would be an Olympic gold medalist or something, super champ. Anyway, the point I'm trying to make is, well, most of us have no idea of capacitance. We don't use it so much that we know about it. So, looking at this value for the Earth and looking at this object and say, if I say capacitance is 2.5 microfarads, it must be a bit of a surprise. You would expect it to be much lower. Let's do another calculation. This time, two conductors of radius R1 and R2, they are far apart, so that you can treat each one of them as isolated. You want to find, they're connected by a wire. You want to find the capacitance of the system of these two conductors. Mind you, they're connected, so they'll be at the same potential. So we assume a charge. If we assume a charge Q on these two conductors, it will spread in such a way that the potential is same for both. So if this has got charge Q1 and this has got charge Q2, since they're connected, the idea for this being treated as isolated is we can ignore the effect of this charge on this object, and when you want what is the potential, since you're ignoring the presence of the other conductor, it's so far away, the charge would be uniformly spread on the surface of this. Potential will be Q1 by 4 pi epsilon 0 R1. So this is Q1 by 4 pi epsilon 0 R1, and this is Q2 by 4 pi epsilon 0 R2. This is the common potential they have. And for the capacitance of the system, we want to Q by V, where Q is Q1 plus Q2. That by V, that's what we want. Now we can replace Q1 in terms of Q2, right? And then V in terms of, say, Q2. Q1 is Q2 into R1 by R2. So Q2 into R1 by R2 plus Q2 by potential V in terms of Q2. We won't cancel this Q2. Q2 by 4 pi epsilon 0 R2. So you would expect this to be R1 plus R2. You simplify this and you'll get this as 4 pi epsilon 0 R1 plus R2. So this is how you find the capacitance. You assume a charge, find the potential, and find the ratio of charge to potential. As expected, when you connect the conductors together, there is more surface area for the charge to spread. So potential will be lower and capacitance will be higher. This kind of result is not a surprise, right?